Welcome to Cryptography Engineering Group Presentation Voice Activity Detection Algorithm. I will start by introducing the team. We are from Group 4 and I am Joe.
Hello there, I am Daniel.
And I am Tasnim.
And I am Abu Bakar Osama. And this is our Cryptography Engineering lecturer, Mr. Syed Hamid Madni. We are presenting a voice detector algorithm that is used to transfer the voice
after detecting into the text to help deaf people to understand without the help of sign language.
Muhammad is a deaf person. He wants to communicate with people who do not familiar to sign language, so Muhammad is using this algorithm to transform his voice into words so Muhammad can understand people who don't know the sign language.
This algorithm is helping in detecting people's voices. After detection, the voice is transferred into words, then he can read the speech as the written word.
The voice is detecting using 1. Break audio signal into frames. 2. Extract features from each frame. 3. Train a classifier on a known set of speech and silence frames. 4. Classify unseen frames as speech or silence. Then speech-to-text technology works by picking up on these vibrations and translating them into a digital language through an analog-to-digital converter.
A phoneme is a unit of sound that distinguishes one word from another in any given language.
The first thing that we need to do is process our audio signal through a high-pass filter that has a cutoff frequency of approximately 200 Hz. This is done in order to eliminate any DC offset and low-frequency noise that may be present. When it comes to speech, there is typically relatively little information below 200 Hz, which is why suppressing the low frequencies won't do any harm.
Before the features are extracted from our audio stream, it is first divided into overlapping frames that last between 20 and 40 milliseconds. Typically, a frame is extracted every 10 milliseconds. For instance, if our audio stream is sampled at 16 kHz and we assume that the length of each frame is 25 milliseconds, then each frame will include 0.025 times 16,000, which equals 400 samples per frame. Since there will be one frame displayed every 10 milliseconds, the first frame will begin at
Once framed, we then extract features from each frame. In the following discussion, is a frame of speech, which can range from 1 to L, the number of samples per frame. The following 5 features are extracted for each frame. 1. Logarithm of frame energy. 2. Zero crossing rate, the number of zero crossings per frame. 3. Normalized autocorrelation coefficient at lag 1. 4. First linear prediction coefficient of a PTH order predictor. 5. Logarithm of linear prediction error from a PTH order predictor.
No one of our features will successfully distinguish between speech and silent frames, but by intelligently combining all of the features, we can reduce the likelihood of inaccuracy. By calculating the mean and variance of the characteristics belonging to silence and the mean and variance of the features corresponding to speech, Rabiner creates a Bayesian classifier. We assess the likelihood that an unobserved frame comes from each label in order to identify its label, presuming that the data is distributed according to the multivariate Gaussian distribution. The frame label is determined by which model has the highest likelihood. A discriminative classifier, such as a support vector machine, is an alternative, SVM. It is very easy to train an SVM classifier to distinguish between speech and silence using a package like SVM. The set of files must have labels that are known for training. This requires a person to review the files and categorize each frame as speech or silent. Although it may be tiresome, the classifier will perform better the more training data it has. The noise in the training files should closely resemble the noise in the testing files, which is a crucial aspect. Try to train with as many different noise types as you can at various SNRs if you can't predict what noise will be present while utilizing the VOD. It is crucial that all of the training samples are recorded on the same channel as the one on which the VOD will be employed if you wish to apply a VOD to telephone voice, for example. Any inconsistency between training and testing will be reduced as a result. After the training is over, you ought to have a model that you can use to forecast the labels of features that aren't visible. Once a model has been trained, we can determine whether speech is present or absent in new, unseen frames of audio. As the amount of noise increases, we expect the accuracy of our VOD to decrease. Sometimes the predicted label can rapidly oscillate between speech present and speech absent. This behavior is usually unwanted, and can be easily handled by applying a median filter to the predicted VOD labels.
The advantages and disadvantages of VOD. Advantages are: 1. Voice commands are a far more efficient tool than typing a message. 2. Voice recognition and speech activation is being developed for a whole myriad of reasons. 3. Lower operational cost. 4. Voice can communicate emotions. Disadvantages are: 1. Difficult to build a perfect system. 2. Speaking is loud and invites noise to others. 3. Filtering background noise is a task and it is too much that can even be difficult for humans to accomplish. 4. This biometric is sensitive to environmental conditions such as background noise.
That's how Muhammad can understand people. That's all from us. Thanks for listening.